All right, so for that first one, when we see cube root of 8, it means what number cubed equals 8. And so that means that the answer here is going to be 2. Because 2 cubed, that is 2 times 2 times 2, equals 8. All right, for the next one, number 2, what's the value of the cube root of negative 8? Now, when we did square roots, we couldn't do the square root of a negative. The question is going to be, can we do the cube root of a negative? Well, the potential answer would be that it was going to end up having to be maybe a negative 2. So let's test that out and see if that works. If I make all of these negative 2's, well, what's negative 2 times negative 2?
Positive 4.
Positive 4. So that means we're doing positive 4 times negative 2. And 4 times a negative 2 is negative 8. So yes, it does equal a negative. So negative 2 cubed equals a negative 8. So that works. So that's going to be negative 2. Number 3, the value of the cube root of 27. Now, I did say you can do each of these without a calculator, right? So you can bet that this is just going to be a whole number. It's not going to be like some weird decimal. So let's try something. What does 3 cubed equal? Well, that would be 3 times 3 times 3. 3 times 3 is 9. Times 3 is 27. Okay, so since 3 cubed equals 27, that means the cube root of 27, yes, would be 3. We can do that. So notice the relationship here, though. The cube root of 27 is 3, and 3 cubed is 27. All right. For 64, I would guess 4 here. So now I'm going to check that. What is 4 cubed going to equal? Well, that's going to be 4 times 4, which is 16. Is 16 times 4, does that equal 64? Yeah, it does. And so since 4 cubed equals 64, that means that the cube root of 64 here is going to be 4. All right, now for that last one. We're going to be doing the cube root of negative 125. Now, can we do the cube root of a negative? Yeah, remember we saw that up here, that we can do the cube root of a negative. And so it's going to be a negative number. And I would think I'd want to try negative 5 cubed. So what does negative 5 cubed equal? Well, negative 5 times negative 5 is 25, positive 25 there. And 25 times a negative 5 is negative 125. Yes, so that works. And so yes, it will in fact be negative 5. So those are each of our answers there. A little side note on something that came up along the way there. Remember that if we square any kind of a negative number, you'll end up getting a positive. But you'll notice here where we saw that if I cube a negative number, I get a negative. We can actually generalize this anymore. Anytime this exponent is even, it's going to give you a positive. Anytime this exponent is odd, if you do a negative to an odd power, you will get another negative. And so you can do those if it's an odd power like that. All right, now, a lot of these kinds of values are going to be coming up a lot in this unit. And so they're going to come up so often that I actually want you to get to know them. Now, with perfect squares, you know the list of perfect squares pretty darn well. Like if I said to you, what's the square root of 144? You can tell me it's 12. But do you know what 12 cubed is? Probably not. The good news is, I'm not going to make you memorize that one. That one doesn't come up all that often. But these do come up pretty often. And so what I like you to do is write these down and make note to yourself that you need to get these memorized, because these are the ones that come up so often that I'm going to expect you to know them by heart. And the cool thing is, by knowing this list, we actually can know a whole bunch of other things just from knowing these facts. So, for instance, if I asked you, what is the fourth root of 81? What is the fourth root of 81? 3. Because what that really means is, what to the power of 4 equals 81. And you can see right up here, we should know that 3 to the power of 4 equals 81. So knowing these facts allows us to know much more. Now let's check in on a couple other ones. What is the cube root of negative 64? Notice 4 cubed is 64, but this one's a negative 64. So it's going to be negative 4. Or similarly, what is the fourth root of 625? Actually, negative 625. What's the fourth root of negative 625?
Negative 5.
Actually,
5.
it's nothing. There's no solution for that one. Why? Because it's an even root. Remember with the even roots, like trying to take a square root of a negative, we can't do it, we get imaginary numbers. Same kind of thing here. So you cannot take an even root of a negative, only the odd roots of a negative. Okay, so that one can't be done. Okay, let's look at one more. What is the fifth root of negative 32? Well, it's an odd root, so yes, you can do it with the negative. And so it would be negative 2. Actually, I said one more, but you know what? I just thought of another one I want to give you. So last one. What is the 99th root of 1? 1. Yep. So you notice any root of 1 will equal 1. And we know that because of this. 1 to the power of anything equals 1. All right. Now, this whole interaction between exponents and their roots, there's actually a lot of information in there that we can generalize. And so we're going to take a look at how we can take some of the stuff you've already seen, some of the stuff you saw yesterday, and we're going to generalize it a little bit. So I'm going to give you an example here. Tell me, what does x squared to the power of 1/2 equal? Yep, it equals x to the power of, well, when I do a power to a power, that's where we multiply the exponents. And you got to have that rule down. You got to know that rule by heart. If you don't have it yet, write it down again so you help yourself remember. Power to a power means multiply the exponents. So I'm going to have to do 2 times 1/2. And 2 times 1/2 equals 1. Well, of course, x to the power of 1 just equals x. So yes, that whole thing just equals x. All right, another example now. What is the square root of x squared? Well, here we're going on some algebraic rules we've seen. We've been talking about how square roots and squares undo each other. And so, since they undo each other, it would just equal x. Now, if you want to get into advanced math, it actually is the absolute value of x and some weird little stuff like that, but we aren't getting into that. We aren't dealing with that little detail right now. It just equals x. All right. But notice what we just figured out. Both of these were x squared. In one of them, I did the square root of it, and in the other one, it was to the power of 1/2. But it was the same thing to both of those. And they both gave us the same answer of x. That means, that must imply at least, that anything to the power of 1/2 is going to be the exact same thing as doing the square root of that same thing. The 1/2 power means square root. And that is a general rule that we are going to actually generalize here in a moment. But I'm going to take it even further because I want to go beyond square roots. So, let's look at x cubed. I want to make x cubed equal x here. So, what would I have to raise it to?
1/3.
Yeah, 1/3. Because 3 times 1/3 is going to equal the 1 here that I want. And of course, x to the 1 is just x. Okay, another way to look at it. What root do I apply to x cubed for that to get x? Which root is it?
Cubed.
The cube root. Because remember, cube roots undo cubes. And cubes undo cube roots. They undo each other. And so that would also equal that from the algebraic perspective. But again, notice what we just showed. We just showed that something to the power of 1/3 is going to equal the same thing as the cube root of that same thing. You know, this is actually the exact same rule. But some of you are looking at it like, yeah, but one of them's a cube root and the other one's a square root. They're different. Well, they kind of are and kind of aren't. What number would I write here in the square root if I were going to write a number in there? A square root is the same as the second root. We just don't need to write in the 2 when it's a square root. Because, of course, in math, you've seen many times, like if I have 1x, that's the same as just x. There's always that one number that we can assume to be there if we don't write it in. When you're writing a radical, if we don't write that number in, it's assumed to be a 2. And so, you notice that it is in fact the exact same thing going on in both cases. Whatever number was in the bottom of our fraction, that's what told us which root it was going to be. Now I can generalize. This should go into your notes. If we have x to the power of 1 over some number, I'm calling it b here, that equals that root of x. Now, the interesting thing is that this is actually just a specific example, a specific case of an even more general rule. And so to see what the other general rule is, we need to figure out what would x to the power of a over b equal. So what if it's not 1 over b? What if it's a over b, some other number on top? How do we do that? Well, I can figure it out by making one fancy little twist here. You play with these long enough, eventually you start saying, wait, if I do this, I can make it look like that. What I want to do is I want to be able to write the whole thing in terms of 1 over b. Well, if I want that to be the same, then it would have to be x to the power of what? It'd have to be a, yeah. Because a times 1 over b equals a over b. And so those are the same. But by writing it that way, it shows me how I can then change it into a form that looks like this, using the same rules what we see up there, because I can now turn it into the b root of whatever is to the power of 1 over b, which is x to the a. Or, to just put it simply, x to the a over b equals the b root of x to the a. So, also have this into your notes, put it there with it, and you'll notice that it really does say the exact same thing, because this second example is just the very specific case where a happens to equal 1. Notice, if a equals 1, then it's x to the power of 1. And of course, x to the power of 1 just equals x. So it works because basically what we're doing is taking this one up here and putting it there. It's just that simpler version of it. So to practice that new rule that we just got, we're going to take each of these 3 different expressions and we're going to rewrite them in radical form. Now notice the vocabulary here. When we say in radical form, that means your answer is going to have a root in it. So that's what we're looking for. So write down each of those 3, and then we'll go through them together to see what they should look like. So for that first one, we have x to the 1/2. We've actually seen that one come up a couple times already here. We know that is the same as the square root of x. Now, if you went about this the long way, you might have started by using that second rule we wrote, and you might have written the second root of x to the power of 1. But actually, this is the exact same thing. Because, of course, x to the power of 1, well, that just equals x. And the second root is square root. When it's a second root, you don't have to write the 2 in. All right, next up, we have x to the power of 24 thirds, where we would turn that into the cube root of x to the 24 if we just blindly follow the rule. But I'm now going to make you think a little bit more, because we're not going to just blindly follow the rule. Notice 24 thirds, it's a fraction. And of course, we're so good with fractions that by now your brain has been trained to look for reducible fractions, and that one does reduce. If you ever have a fraction that reduces, reduce it at the start. So the 24 thirds, that reduces to just equal 8. So I can start by turning it into x to the power of 8. Now the instructions here say write each expression in radical form, which I said means you got to have a radical in your answer. Well, that's only if there's still a fraction in your exponent. If there's no fraction left, you just stop there. X to the 8th is as simple as it gets. So that's your final answer, that's it. All right, and then for that last one, it's x to the 3/4. Notice the fraction, it doesn't reduce at all. And so I know I'm going to end up as a radical. Which number always goes in the radical here?
The denominator.
Yep, it's always the number on the bottom. It's our denominator every single time. So it's going to be the 4th root of x cubed. And that's it. That's our final answer. You're done. All there is to it.
This one's just x.
So next up, we're going to do the same basic process, but we're going to go in reverse. In this case, it says write each expression in exponential form. When I say exponential form, what I mean is that your answer is going to be like x to the power of something. Exponential form has no radicals in it. So it's basically saying change it from radical form, where it is now, into exponential form. All right, now that first one, the cube root of x, we've actually seen that one before. But let's see how we'd go about thinking about it. It ends up being x to the power of a fraction. Because I have a radical, I know it's going to be a fraction. Now the number on the bottom of the fraction is always whatever root it is. And so we know that number has to be the 3. But the number on top is always whatever the exponent is on the inside. But there's nothing written there. So what is that number? 1. And so then this is x to the 1/3. All right, next up, we have x to the power of 8th, and we got the 4th root of that. So that would be x to the power of a fraction again. The radical always tells us which number goes on the bottom. So that's our 4. The exponent is always the number that goes on top. So that's an 8. But notice we're not going to stop there. What does 8/4 equal?
2.
So yeah, we turn it into then just x squared. Simplify that fraction. Remember, anytime you see a fraction, look to see if it can be simplified. And if you get that idea down, it's actually going to make a lot of the work that we're going to go into later actually a lot easier as well. All right, last one. Well, again, we start with a radical, so I know I'm going to end up with x to the power of a fraction. The radical goes on the bottom. The exponent goes on the top. And so you end up with x to the 2/5. And that's it. And so yesterday we did that card sort activity, and we were kind of trying to match up these different forms. Now you can start to see how all those worked out. And so if you had a little trouble with it or didn't quite get the idea, now you got it. A couple little details to look out for here. When you write these radicals, note that that number that tells us which radical it is, which root it is, it always is going in the crook of that radical sign. It's not going to be written like this. That means something different. This means 5 times the square root of x squared. If you want it to be the 5th root, you would actually have to squeeze that 5 up in here. Okay, so just be careful when you write them out so you can be disciplined on it and not cause yourself problems later. All right, now that we've done those problems, which are just abstract using that information, we now can see how we can figure out each of these 3 values without even having to use a calculator. So take a moment, write down each of the 3, and then we're going to walk through the process about how we can think about and approach these to do them without a calculator. Now for most people, looking at it just in this form is pretty tricky to do. But if we change the form a little bit, it all of a sudden makes it very doable. Because, of course, we know that the power of 1/3 is the same as the cube root. So when you take a look at that first one, what you're really going to do is you're going to say 125 to the 1/3 is actually the cube root of 125. This now is a much easier problem to solve. Because, remember, the cube root of 125 means what number to the power of 3, that is, what number cubed, equals 125. Well, what number is that? 5. Because that's one of our values that you wrote down earlier, one of those values to memorize. 5 cubed equals 125. And so the answer then is 5. All right, next up, 4 to the 5 halves. I'll give you a hint here at the start. The answer is not going to be 10. That's what you get if you just did 4 times 5 halves, which at the very start, when people first see these types of problems, is sometimes a temptation to do. It's not that. It's actually the square root of 4 to the 5th, which right now, as you look at it, though, doesn't seem very helpful still. Because if you look back at that list of numbers where you need to know these values by heart, 4 to the 5th is not one of them. But there's a little trick to these that we can use to our advantage. Because I've been, so far, putting all those exponents on the inside, but there's actually nothing magic about doing that. We could also put the exponent on the outside of the radical. It means the exact same thing here. So, as you take a look at these two different ways of writing it, and it's not that you have to write both of them. What you're going to do is think about which one of those is going to be easier to do and rewrite it that way. So, do you know what 4 to the 5th is off the top of your head without a calculator?
Yeah.
A few of you maybe yes, but most people probably not. Do you know what the square root of 4 is off the top of your head?
Yes. 2.
Yes, everybody should know that one. The square root of 4 is 2. So I'm going to use that form. I'm going to take the square root of the number first, which is 2, and then I can figure out what is 2 to the power of 5.
22.
And 2 to the 5th, that is one of those on your paper that you wrote down that we should know by heart. 2 to the power of 5 is 32. And so notice, by just manipulating these forms, we can figure this stuff out without having to rely on the calculator. All right, next one. We're doing 27 to the 2/3. And again, you can write it as a radical. Change it into radical form if you're trying to do one of these without a calculator. Now, there's two different ways you can write it. You can put the squared on the inside or the squared on the outside. Which of those do you know? Do you know what 27 squared is? At least without a calculator. Do you know what the cube root of 27 is? Yeah, I hope you know that one.
33.
So we set it up, we think about, okay, which form is easier to do without a calculator? And then I choose that form. Now, if you're writing this out on your paper, you actually don't have to write this one out because you didn't use it. You can if you want to, just kind of keep track of everything, but you don't strictly have to. So I did the cube root of 27 first, which was 3, and then I could just do the 3 squared, which is 9. So we're going to wrap up by doing these two problems. Because these are two problems that would have been impossible to do before today's notes. But by using today's notes, we're actually going to be able to do these. All right, so in order to do these, first of all, we cannot just multiply them as radicals right now. It's not like I can just do 3 times 9 and then do x squared times x. That doesn't work. The reason why it doesn't work is because they're different radicals. One is a cube root and one is a 9th root. So what we can do, though, is we can change the forms up. I can change each of these radicals into exponential form. In other words, writing each one with a fractional exponent. If I do that, it becomes x to the 2/3 times x to the 1/9. By doing that, we now can actually do it, because when multiplying x's, what do I do with their exponents? we add the exponents. And again, if that rule is one that you don't quite remember, make a big note of it. Write it down your paper again. Remind yourself of it, because it's going to come up a lot. You got to remember that one. So when I multiply the variables, I add their exponents, which means that in order to figure out this, I'm going to have to do 2/3 plus 1/9. Yes, you still have to be able to operate on fractions. In order to add fractions, what do we always need to get? Common denominator. Which, if I'm looking at 3 and 9, the lowest common denominator I could use would be 9. Yes, you could go up to 27, but you're going to have to do some reducing at the end. So I'm going to use 9, which means multiplying the top and the bottom of that first fraction by 3. And if you now have 6/9 plus 1/9. Now you can go ahead and add them. Remember, when you add fractions, you need a common denominator because the denominator stays the same. That's one of those great rules of math. You can generalize to so many things. If two things have to be the same, it's because that part is going to stay the same. So I add the tops, the bottom stays the same, so that whole thing equals 7/9. Which means that when I do this multiplication, I add these, and I get x to the 7/9. All right, now the question is if we're done here, and the answer actually is no, because simplified form, when we deal with exponents, means there's no fractions left in the exponents, just like there should be no negatives left in the exponents if it's simplified. And so the very last step we're going to do is we're going to take our fractional exponent and turn it back into radical form. And so I'm going to write it as a radical. Which number goes into the root here?
9.
Yep, it's the bottom of the fraction, so it's the 9 here. And so then that means my final answer is the 9th root of x to the 7th. And then this one is done now. And that's the whole process for how we multiply radicals. All right, next problem. Over here, we're dividing. Well, I can't do it right now, though. I can't do it with the radicals. So I got to get rid of the radicals. And how do I get rid of the radicals? Turn them both into exponential form. And when you rewrite each of those as a fractional exponent, this is what you should be looking at. We got x to the 5/6 over x to the 1/2. Now some of you might be looking at this thing and that's a lot of fractions. Yeah, but just remember what each one is doing and it'll help you out. Like this fraction right here. Remember, when you have a fraction, it really means division. So you're doing the top divided by the bottom. And when we divide x's, what do we do with their exponents? We subtract them. Another good one to make sure you have down, that you have memorized, and write it down if you forget that one. When you divide variables, that means you subtract their exponents. So dividing variables means subtract the exponents. And so that's what I'm going to have to do here. I'm going to have to do 5/6 minus 1/2. And now again, it's just a fraction operation. So again, I'm going to need a common denominator. Between 6 and 2, looks like 6 would be a nice easy denominator to use. So I'll turn it into 5/6 minus 3/6. And then we can go ahead and do the subtraction. Remember, the denominator stays the same. So I get 2/6. But I don't actually want to stop there, because you'll notice 2/6, again, we should be attuned to looking at our fractions and seeing, can it be reduced? And it can be. 2/6 reduces down to 1/3. Okay, so I did all of that subtraction here just to figure out how to combine those x's. It means that after I get x to the power of 1/3. And if that whole thing equals x to the 1/3, again, I want to leave my answer in radical form. I don't want a fraction left in my final answer. So we write our final answer as the cube root of x. That's then your final answer. You're done with that one.